Hello everyone, I am Anindya. I will be presenting our work, a visual active search framework for geospatial exploration. This is a joint work with Michael, Scott, Jiarui, Roman, Nathan and Yevgeniy. Let's first define the problem of visual active search. Let's assume we are given a large geospatial search area as an image. We first divide the entire search area with non-overlapping equal-sized subregions. There exists a set of subregions that contains one or more instances of the target object we wish to search. We denote such grids or subregions as green plus sign. But we do not know which subregions contain the target object a priori. But we can make successive queries where each query corresponds to observing whether the object we are searching is present in that particular subregion. So the utility of a set of observations or query to be the number of subregions found that contains a target object. We can simply represent the utility as U of D, where D is the set of observations we make. So UD equals the sum of the query outcomes. Note that query outcome is 1 if the query is successful, otherwise it is 0. A query is successful if the queried subregion or grid cell contains one or more instances of the object we are searching. So the objective of visual active search is to maximize the utility, which is defined as the sum of true levels of the query outcomes, such that we are allowed to query sequentially until the search budget exhausts. We mathematically formulate this objective as a constraint optimization objective as shown in the slide. Here, Qt denotes the index of the subregions we choose to query in step T. Cjk be the cost of querying the kth subregions if we start at jth subregion, and C is the total query budget. Our ultimate objective is to learn a search policy that makes use of a leveled dataset of past search tasks. There are numerous applications of visual active search ranging from detecting poaching activity to human trafficking, broad area search and rescue, identifying landmarks and many others. Consider a large national park that hosts endangered animals, which are also in high demand on a black market, creating a major poaching problem. An important strategy in an anti-poaching portfolio is to obtain aerial imagery using drones that helps detect poaching activity, either ongoing or in the form of traps laid on the ground. The quality of the resulting photographs, however, is generally somewhat poor, making the detection problem extremely difficult. Moreover, park rangers can only inspect relatively few small regions to confirm poaching activity, doing so sequentially. Crucially, inspecting such regions yields new ground truth information about poaching activity that we can use to decide which regions to inspect in the future. We can distill some key generalizable structure from this scenario. Given a broad area image, sequentially query small areas within it, with each query returning the ground truth to identify as many target objects as possible. The number of queries we can make is typically limited, for example, by budget or resource constraints. We refer to this general modeling framework as visual active search. Suppose we look for small cars in an image, as shown here, starting in the grid marked start, which we initially think is the best place to look. The greedy policy, being a one-shot predictor of likely grid cells containing the target, continues to explore similar regions marked as crossed circle. What this approach ignores, as does framing the problem as traditional one-shot object identification, is the fact that both success and failure of past queries are informative due to complex spatial correlation among objects and other patterns in the scene. Here, because the car was not found, we proceed to instead explore regions that have somewhat different characteristics. The key to visual active search, therefore, is to learn how to make use of the ground truth information obtained over a sequence of queries to decide where to query next. Also, a good visual active search strategy must learn an efficient exploration-exploitation strategy. Why? Let's assume we start in the grid marked as start. We might think it is a bad decision to query in this grid. However, recognizing that this grid does not contain the target becomes valuable in subsequent decision making stages. Knowing that the start grid does not contain the target implies that similar grids also do not contain the target, preventing unnecessary queries in those similar regions. We model visual active search as a Markov decision process. In this MDP, the state includes input features of entire search space. The state also includes outcomes of past search queries generated as O. Each element of O corresponds to a grid cell. For example, jth component of O corresponds to grid cell J. If jth grid is not queried previously, we assign jth component of O to be 0. If jth grid cell has been previously queried and it does contain the target, we assign the jth component of O to be +1, otherwise it to be -1. And the final component of input state includes the remaining search budget B. The policy network first extracts the features from the given input image and then combines the extracted latent features with the search related information such as previous query outcomes and remaining search budget, and feeds that combined information to a grid prediction network which determines the next grid cell to query. Hence, the action in this MDP corresponds to selecting a region from the set of unobserved regions or grid cells. We assign a reward of 1 if the selected region contains a target, otherwise we assign a reward of 0. The state transition corresponds to updating the knowledge of the environment after observing the outcome of the query. Specifically, we update the representation of previous search outcomes O and reduce the search budget by subtracting the current query cost from the remaining budget. Our final objective then becomes to learn the parameters of the policy network that maximizes the total expected reward of the entire search. Note here, theta represents the parameters of the policy network. We leverage the reinforced algorithm for this purpose. We compare the search performance of our proposed method with the baseline in terms of ANT, which is the average number of targets discovered across the search task. In this table, C denotes the search budget, N represents the number of grid cells for the corresponding search task. We observe significant improvement in performance compared to the baseline across different experimental settings. Here is a comparative exploration behavior of VAS and greedy policy with small car as a target object to be searched. We can see that greedy policy makes similar mistakes multiple times, whereas VAS initially makes a mistakes but leverage the information from the query outcomes efficiently to adapt its search strategy that ultimately results in discovering more target grids. Here we show the exploration behavior of VAS for different target types. The first row corresponds to large vehicles, the second row corresponds to small car, and the third row corresponds to ships as the target object to be searched. Also note that each row captures the query sequence and corresponding heat maps obtained using VAS as different stages of search for the corresponding target types. Note that darker grid indicates higher probability of search. We can see the exploitation behavior in this search strategy. For example, in the top row, VAS initially explores regions with different semantics such as rooftop, but later on focuses mostly on the road to discover regions that contain large vehicles. Here we show how the exploration strategy of VAS is influenced by previous search outcomes. We call it sensitivity analysis of VAS. The top row depicts the query sequence and corresponding heat maps obtained using VAS. Note that the darker grid indicates higher probability of querying to that grid cell. Middle row corresponds to a similar result while enforcing the query outcomes at every stage being unsuccessful, irrespective of true query outcomes, by updating the corresponding component of the previous search outcome as -1 at every search step. Note that as search progresses, VAS keeps on exploring regions with different semantic features as it realizes that it always query in the wrong grid from step 1. Hence, always explore to a region with different semantic features and never exploits. And bottom row corresponds to a similar setting while enforcing the query outcomes at every stage being successful, irrespective of true query outcomes, by updating the corresponding component of the previous search outcome as +1 at every search step. As a result, now VAS continues to explore regions with similar semantic features as it realizes that it always query in the right grid from step 1, hence never explored to a region with different semantic features. Such behavior shows the influence of previous search outcomes on exploration behavior of VAST.